So let me introduce the speaker, Mike Ludkovski. He is a professor and a colleague of statistics and applied probability at University of California, Santa Barbara, where he co-directs the Center for Financial Mathematics and Actual Research with Jean-Pierre. Among his research interests, he has been doing a lot on Monte Carlo techniques for optimal stopping, stochastic control, modeling of renewable energy markets, Gaussian process models for quantitative finance, and so on. And so he'll be talking today, machine learning surrogates for parametric and adaptive optimal executions. If you have any questions from audience, please write your questions on Q&A. And Mike, the screen is yours, please.
Thank you to Moike for the very nice introduction. I'll be talking about work that has been, I keep doing with Tao Chen, who was a visiting professor at UCSB. Then he went to Michigan, and now he is at QRM, which is a consulting company, and he's actually based in Singapore right now. And then Moritz Voss was another visiting professor at UCSB, who is now at UCLA. So to outline what I'll be talking about, so the theme will be optimal execution problems, and I'll explain this in a second, specifically with stochastic resiliency. But really, what I'm trying to convey today is different types of control formulations, in particular thinking about adaptive and robust formulations, and how using surrogates, statistical machine learning tools to handle them in unified manner. And I think it creates a very nice sandbox for experiments, and also it's a nice pedagogical setup to try out different ideas of how to combine stochastic control with neural networks or other machine learning techniques. So in this talk is actually a summary of two different papers, one which has been submitted and should be accepted soon, the other one which is still not publicly available. All right, so let me jump into the problem formulation. So we're talking about optimal execution problem. So that means we have a large trader who needs to buy a large number of shares, and he's incurring price impact. I'll be talking about a buying problem. So he wants to buy X0 shares over n time slices. And so what I'll be talking about next is kind of standard. So I'll go a little bit fast. This is really kind of recapping what's been done for the last decade or so, and I'll have those references in a couple of slides. So first we have the unaffected price, which is what would happen if there was no trading happening. And then we're going to see what the actual execution price looks like, which is going to be the unaffected price with a offset. So there's a deviation D process, okay, which is how the execution price compares to the mid price. Now the mid price has also permanent price impact gamma. Now that term is going to disappear, so I'm not going to talk about gamma ever again, because that's going to be a unavoidable expense, and so it's only part of the optimization. Now this deviation D, this is kind of capturing the resilience of a limit order book. It has the following dynamic. So this is the key equation to it. I want to explain the terms. So the deviation D, and we're in discrete time. So, but you can imagine this is a discretization of a continuous time setup. So there's the first term says that there is a resilience effect where at rate kappa, the deviation goes back to zero. And remember, the deviation is something you have to pay extra. So you want deviation to be small rather than big. So the deviation mean reverts back to zero at rate kappa. That's the first term. Now the second thing that happens is a transient impact, which is when you trade UN shares, then there is a power alpha, which is how much the D moves up. So that's how much you kick the deviation up by instantaneously trading. That's essentially how much you're eating into the limit order book. And now the third term, which is not so common, is that this process D is stochastic. So it has just stochastic shocks. And one way to think about this is that the depth of the book can fluctuate. And so the deviation can increase or decrease. You can also imagine this as capturing the effect of other traders who are also trading at the same time as the large trader. and they're slightly affecting how this D process evolves. Okay, so but overall we have a kind of a Ornstein loopback dynamics. We have a mean reversion to 0. We have stochastic noise, and we have the impact of our trades. So which has, again, two terms. It has two parameters. It has alpha, which is the price impact power. So typically people think alpha is around 1, maybe a little bit less than 1. So it's a concave price impact. And there's eta, which is essentially how deep the book is. So large eta means that the book is sensitive to your trades, where small eta means it's non-sensitive. So the right way to think about eta is 1 over, which is basically how the depth in terms of typical order size of the book. Okay, so the D is going to be one of my key state variables. The other key variable is going to be X, and X is just going to denote how many shares I have left. Remember, I'm trying to buy, and so I'm just keeping track of how many left. I had to originally I had to buy X0 shares, and now I have Xn left. All right. So the goal of my implementation problem is the standard goal of trying to minimize how much money I have to spend to buy up those X0 shares. So that's going to be my main objective, is to minimize the cash cost. And then I'm going to have another term I'm going to add. I'm going to have an inventory risk term, which we'll see in the next slide. So this equation, this is really kind of a bookkeeping, so I don't want to go into those details, but essentially it says that your cash evolves according to how much you're paying, which is you have the mid price M, and then you have this deviations D, and there's some averaging between dn minus 1 and dn. This is just to have the correct accounting in terms of what happens sequentially in discrete time. This is not an issue in continuous time, but you have to do it the right way. And what happens here is actually we're averaging out. So we're saying that the deviation is sort of split into two halves between last period and new period. But effectively, it says that your trading costs are linked to the mid price, which is going to be martingale, is going to go away, and then the deviation dn, and that of course gets multiplied by the volume of your trade un. Okay, so this is the last equation here. This is the overall, as a sum, the overall cash balance you're going to try to minimize. So this is pretty standard in the literature. This is what people call a transient price impact. The only new feature, which is not so common, is to have the stochastic resiliency, is to have D as a stochastic process rather than just keeping track of what you did in the past. All right, so the classical formulation is to say, well, I have I'm given all those parameters which I highlighted, so I have quite a lot of them, and here's one more. So I have, in terms of parameters, I have kappa, which is the resilience rate. I have eta, which is the instantaneous price impact. So it's 1 over 8 is kind of the book depth. I have alpha, which is the power of the instantaneous price impact. And I have one more, which is nu. Nu is penalizing me for carrying a large inventory. So this is some kind of a price risk term or inventory term, which if nu is positive, then it spurs me to trade faster so that I don't keep a large inventory around. So this is some sort of an urgency penalty. You can think of nu to be 0. This is the sort of the classical case, but it's kind of it's a free sort of add-on, and several people considered this before. So in my first formulation, I'm just trying to minimize my overall cost. So if you look back, this expression here for my dynamic programming equation is essentially just keeping track of Cn. The first two terms go away because they're either constants, they're not depending on my strategy, or due to martingale property of the unaffected price. And what's left is the last term here. And again, epsilons are mean 0, so it's also going to disappear away. But that's the term that shows up in my dynamic programming equation. Okay, so again, this is all pretty classical. The only slight twist is that I'm going to insist on having only buy strategies. So I'm going to insist that U has to be non-negative. Okay, so again, I'm going to just write down the programming equation linking Vn to Vn plus 1. And again, here what I'm trying to do, I'm trying to minimize my buying costs. I have a minimum over the control U, and U has to be between 0 and X. This is saying that I'm buying, and I cannot buy more than how much I have to buy total. So that's the two bounds. Okay, so this is a pretty nice looking stochastic control problem. In particular, if you stare through everything, you can see that when alpha equals to 1, this is a linear quadratic control. So, and this is kind of the starting point to have some nice computations involved. Okay, now just to orient how this connects with literature, so there's a long list of papers I've looked at similar models. So effectively, the model I just talked about is generalization. So it nests a bunch of previous models. So Obizhaeva and Wang was the first one who had this setup of transient price impact. There were many other folks since then. I think I'll come back to the two papers here by Laurier and Lehal, as well as by Ure. These are more on the computational side, but I think if you want to get the best current state of the art on this literature, there's a new book by Karen Webster which just came out this year, and it does a really great job of summarizing what's known. Okay, so in the first paper that I'll have a archive link at the end of my talk. We actually have an explicit computation. So if you take alpha to be 1 and you assume there's no restriction on UN, then you can actually solve everything explicitly. So I should not take any credit for this. More is that it's a bit of a tedious computation, but essentially you know that everything's linear quadratic, and you exploit that, and you just plug in the ansatz and you crank the algebra, and you get the difference equations, and you have these recursions, which are quite nasty. So I don't claim that you can really see any structural understanding of what happens from these 3 recursions for the coefficients. Again, so the ans, bn, and xn show up as the coefficients of my quadratic ansatz for the value function. So again, my 2 state variables are x and d. So therefore, I have 4 coefficients to care about, and it turns out that the constant coefficients are actually just linked to the sum of these coefficients of d squared. And the d term disappears completely. So this is the answer. And again, so you can also do the same thing for, of course, for the strategy. So you have everything in closed form through this difference equations. And really, this is just generalizing. Again, it's a nice computation, but it is generalizing the special cases that people have already computed before, actually quite a while back. So if you kill the sigma. So if you make the resilience non-stochastic, deterministic, and you kill the inventory penalty, then you get a solution from Obizhaeva and Wang. If you also set D0 to B0s, and this is the famous U-shaped curve, which says that you have a large first trade, you have a large last trade, and you have a constant trading rate at the middle. This is essentially saying that you want to keep your deviation process D constant over time steps. And so you can look at this as a well-known result from Alfonsi et al. In 2010. Now, so essentially, this explicit solution we have in this first preprint is doing 2 things. It's adding the stochastic resilience piece, so having positive sigma, and then it's also throwing in the urgency penalty nu to be positive as well. So the one thing I want to point out, which is quite nice, is the fact that once you have stochastic resilience, then of course, right, you obviously have that the strategy is in feedback form, so it's also stochastic since it's in feedback of dn, and so you wonder how that would compare to a deterministic strategy, such as here, right? This is a deterministic strategy which just gives you a open loop formula for what the trade should look like, and the answer is that due to the linear quadratic structure. Again, it's not completely obvious if you stare at the equations originally, but after you see the pattern, you can prove it that what happens that the order amounts are actually Gaussian, centered around the deterministic solution. So sigma just essentially randomizes how much you trade, a little bit more, a bit less, depending on how D moves a little bit up, a little bit down on average. So cross-sectionally, you just have a Gaussian distribution at the same average value compared to the deterministic one. So one important factor to point out, and this is known from a stochastic resilience literature before us, is that you have this issue that because D is stochastic, what can happen to you is that essentially the deviation, without you doing anything useful, the deviation will move in your direction, right? So essentially the other traders or the noise in the market will decrease the deviation. And the deviation can be in principle positive or negative, right? It just has this linear mean reversion trade. And so what happens is that for specific parameter values, you can have what's known as profitable round trip strategies, which is equivalent to saying that the value function when you have no inventory is actually negative, so you can make money out of nothing. So this is kind of not mathematically satisfactory. This is one reason why I restrict to having buy-only programs. Practitioners generally don't worry about this issue in principle too much. There's several potential solutions to this. One would be to this is all based on having linear price impact. So as long as it's non-linear, this is possibly goes away, particularly if it's concave. And secondly, you're not doing market making. This wall model is supposed to be for a large trader who has a large order to execute. So you don't necessarily care what happens when you have no inventory left. But this is a feature of stochastic resilience models in general. And so therefore, our solution is just to restrict from beginning to buy-only programs. Being less than or equal to 0. Okay, so this was essentially a very quick summary of the first paper, and now I want to talk about the ongoing work we have, and this is trying to modify the basic story. Okay, now what would be a fundamental objection to this model I presented? Well, the objection would be that there's quite a lot of parameters floating around. I have a half a dozen Greek letters, and how would you ever calibrate them in practice? Okay, so there's different arguments, how this might look like, but certainly, for example, the kappa and eta parameters, which are fundamental to the solution and to the dynamics of the system. Again, kappa is about the mean reversion rate, and eta is the instantaneous price impact, how much you move D by trading. Those are not something directly observable. Those are latent things, so you have to somehow learn them, right? So you have to, one way or another, you have to learn them from some kind of data. And so you can, imagine that, in fact, you combine learning with trading simultaneously. Okay, now in the setup I just had, it actually works out quite nicely from a statistical perspective, because we have linear dynamics for D. So we have this possibly nonlinear price impact here with the alpha. But in terms of the two parameters I just highlighted, kappa and eta, the D is linear. And so therefore I can use standard linear regression to estimate, or even better, to update my guesses about what the kappa and eta look like right now. Okay, so I'm kind of combining two different financial ideas. The idea number one being that I have an unknown linearly driving parameter in my model, and I need to learn it. And the second idea is that my market is somehow non-stationary, and so the market is evolving, and therefore I need to keep updating my estimates. I cannot just pretend it's done once and for all, right? So the objection to the first idea would be, well, you did not just start trading today, you've been trading for a while, so why do you have to keep learning? Well, the answer is the environment is non-stationary somehow. Okay, so the adaptive control would modify my previous classical formulation by saying that instead of putting in kappa and eta, what I have to do is that I first try to get this my current guesses, kappa hat and eta hat, and then take those and plug them into the controller, the feedback controller I just described. Okay, so that's directly shows how new information which I get from trading. So this is, again, this has now has the trading also gives me information about what my how my deviation process evolves. I directly incorporate it for the next trade. Okay, so to do that, right, so we'll be able to implement this adaptive idea, again, which is actually very standard in across engineering and financial industry is I have to be able to compute my estimates, kappa hat, theta hat. Okay, so this is will be straightforward for my situation because it's a linear regression, and I'll have equations in a few slides. But secondly, I have to be able to plug them into a function, and so I have to plug in my estimates into something, right? So into here. Okay, so I have to be able to know my control across a range of model configurations, and that's exactly what parametric control looks like. Parametric control says I don't want to solve for to find my strategy for a fixed parameter set, but I want to have it across a whole range of parameters. So effectively, I want to augment my state space, which originally was X and D, which are really stochastic state variables, with model parameters, because I need to understand how my strategy depends across those model parameters as well. Okay, so this was the motivation to do parametric control for, and so we're going to do it using neural networks. So here's how this would look like. So we're going to take we're going to redefine what state variable means for us. We're going to call this Y now, and just for the next 5 minutes, I'm going to define Y to be a tuple of 4 things, which again, my X and D, these are my 2 real state variables, and then as well this kappa eta, which is the ones I care about, the 2 parameters I really care about at this point. And so now I have a 4-dimensional state, and I'm going to construct functional approximations which map this Y's into either the value function or the control strategy. Again, so effectively, I'm trying to solve a whole range of control problems all at once. Now, I showed you that in a sort of special situation when I had linear price impact, alpha equals to 1. So let me go back here. When alpha equals to 1, and when there's no restriction on U, so that when U was not restricted to be only positive, I had a formula. Okay, now I imagine this formula, first of all, it's a little bit tedious, so it's fast, but it's not that nice to work with. And secondly, I want to be able to also handle cases when alpha is not equal to 1, or where I really am restricting to buy only problems U and being strictly non-negative. So I'm going to construct functional approximations to handle this generic situation with the value function of the optimal policy. Okay, so the proposal will be that any functional approximation really can work, but we're going to use neural networks specifically. One reason is because we just wanted to understand how neural networks behave in this environment and what kind of pitfalls or tricks you have to do to make this work. So here's the plan. So first, I have my new state variable Y, and I have to define the transition function for Y. Now, what happens is I start with my my state today. I make an action U, and I have exogenous shock epsilon. These are the 3 ingredients going together, and then I get my new state tomorrow. So this is the transition map. And what happens is the first 2 terms change. So my inventory changes is affected by the control. My deviation D is affected by the control and by the exogenous shock. And then my kappa and eta do not change because these are static parameters, so I just carry them around. Okay, so I have a very degenerate transition function where in fact I only have 1 exogenous stochastic shock. So there's a 1D noise coming into this 4D state, but I don't really care from a numerical perspective. Okay, so and then I'm going to go ahead. I'm going to implement my dynamic programming equation using functional approximation. So I'm going to stick as close as I can to dynamic programming, just putting in hats, which represent my surrogates, my neural network emulators, whenever I see a V or a U showing up. Okay, so here's a terminal condition. This is which is given explicitly for in my case. So this terminal condition here says that at the last step, since I have a hard constraint to buy exactly X0 shares, at the last step, if whatever I have left, I have to just go ahead and buy it, and I have to be done. So this is basically saying almost sure to satisfy the constraint because I have this discrete time steps. It's a very trivial terminal condition. Okay, and now so here's how I'm going to do the dynamic programming backwards. So here is my main equation right here. Okay, so this is my main equation for exactly copying dynamic programming. Now, what I'm doing, I keep the first row is essentially just representing the impact of the control. The second row is the conditional expectation of the value function tomorrow. So I'm really copying over the dynamic programming equation that I had before. Now, again, my state is called y. So now I have to look at the new y after the impact of the shocks. So that's why I have this transition map G showing up here. Okay, and then the value function in the next step is coming from my surrogate. So to get this term here, I'm going to be using my surrogate from the previous step. Okay, so I'm going to build a sequence of neural networks capturing v hat n plus 1 as n changes. Okay, and now the last bit I have to explain. Okay, so how I'm going to actually do this? So get this over here. So I'm going to represent the conditional expectation through a quantization. So I'm going to just replace it by a finite sum, where again, because I'm exploiting the idea that my epsilons are exogenously specified, so I can directly do a sort of a Gaussian quadrature and place it's the integral over the distribution of epsilon by a finite sum with pre-computed weights. So I have my weights W and my special knots EJ. So again, for Gaussian, for example, we can use the pre-computed W's and E's from Pages et al. 2004. So I just approximate the conditional expectation with a finite sum, and then I have to do the minimization. So this is a 1D f min type function, right? So I just minimize numerically over a finite domain. So this is about as easy as it gets for a minimization. So I want to emphasize I'm keeping the logic of my programming in place. I pointwise take the minimum, the local minimum, which as my programming implies, and to have the step ahead value function, I use the surrogate from the previous step. Okay, now what I do, I save actually two outputs. I save both the inf and the arginf, and the arginf gives me the local control, and the inf gives me the local value function. Okay, so now I do this again and again. I have a large collection of training inputs. Okay, m of them. Okay, so imagine m is I don't know, a few thousand, and then I do this. So I solve this step 2 for 8,000 times. So that's 8,000 1D optimization problems in the spirit of dynamic programming. And then finally, as a last step, I just take those training set, my inputs, y's, and my outputs, and I have 2 of them. I have one training set to get the value function back, and one training set to get the controls back, and I train function approximators. Okay, again, we use neural networks, but in principle, you can use anything you like. So if you could train some kind of a tree-based surrogate, you could train a linear model, splines, whatever you like. Okay, so we are just go ahead, and once we have those training sets computed, which again are coming from this local problem, then I go ahead and I go to the last step of the machine learning task of training the functional approximation. Okay, so I want to contrast. So the method is similar, but not to what this paper by Hure et al. With Nguyen Pham and forget the other co-author, but this is about Nicolas Langrenay. So they have several methods in those two papers, but this is what they call a hybrid scheme, where there was a similar idea for generic stochastic control formulation. Okay, so essentially what happens is, and this is why we like this method is twofold. So one, the neural networks are generally dimension agnostic. So the neural network doesn't really care if you give it a 2D problem, a 4D problem, or a 6D problem. From this algorithm is not affected by this dimensionality directly. Of course, they'll be affected by how long it might take to train a surrogate, but otherwise the actual dimension of the input is irrelevant. And that's quite nice because I can start with the classical problem, which has two variables, x and d. I can now augment with kappa and eta to make it four variables. I can go ahead and augment more. For example, I can train across a range of alphas, which is the the powers of the price impact. I can trade across a range of news, which is the urgency penalty. I can have, for example, a 6-dimensional problem just by adding and throwing in a few more things. And the neural network, again, will take probably longer to converge, but otherwise has minimal changes to the code. So that's one reason why neural networks are convenient, because they don't really care about the input dimension, specifically from a coding perspective. And then the statistical formulation, we like it a lot because it's very easy to follow, and it's directly copies over the programming logic, and you can directly see, right? You can look at the V and U values as training inputs. Again, you can see that essentially all you're doing in the last step is just connecting the dots. You're just interpolating between those train locations to get the whole shape. And so this is a big difference compared to the other approach to using neural networks, where you first postulate that the control strategy as a strategy is a parameterized function, parameterized in terms of a neural network, right? And so in that formulation, you do gradient descent, but you don't have the idea that you have a pointwise optimization to ever solve. So we spent actually quite a bit of time to have a nice notebook. So this is completely self-contained. Besides being able to have TensorFlow installed, this runs as is, and so you can easily sort of have a 1-hour class going through this for graduate students to see how you start using neural networks in a stochastic control formulation. And because everything is discrete time, it's very easy to explain. You don't have to get into an AGB equation and things like this. Okay, so if you wonder how well this works, well, this works pretty well. So again, in the case where alpha equals to 1, we have we can take the parameter such that the restriction for u to be non-negative is basically superfluous, and so we can have essentially a closed form benchmark to compare against, and the answer you get is very, very good accuracy for a neural network. So, are there any tricks? Well, there's some tricks for sure. So one trick, which is actually quite important, is that you don't want to learn UN, which is something sort of on a large scale and kind of not bounded in an obvious way numerically, and instead you want to learn the Bayesian ratio UN over XN, which is always between 0 and 1. So how many more shares of given your inventory you want to buy as a fraction? So that makes a big difference for the training. Okay, so formulation number 1 was the case of just classical thing where you have parameters which you somehow calibrated, then you just go ahead and you think about the stochastic variables. Formulation 2 was about being adaptive, trying to learn the parameters as you go, and using those, plugging those in. Formulation 3 says, well, no matter what you're going to do, you don't have exact values for kappa and eta, and so you obviously have some model risk involved, right? So you might have a estimate, but you don't actually know what kappa and eta are. So you want to be able to hedge against misspecification, and I'll show you in a couple of slides. This can be quite severe, and so you want to do some kind of a worst case consideration to make sure that you don't have you're hedged against this model risk. Okay, so how would that look like? So essentially, you say instead of plugging in kappa and eta as either as your expert opinion or as some kind of a statistical estimate, what you want to do, take some kind of worst case to maximize over an uncertainty set B, and then use that to find the worst case parameters. Again, I keep talking about kappa and eta, the worst case resilience rate and the worst case Sinus price impact, and then applies the corresponding control using those worst case parameters. Okay, so here is how this would look like. So I'm not sure if I can draw on this thing well. Let me try this. It doesn't work. So this is this I have. So here's my kappa, and this is my eta. So these are my two parameters. This is a value function from it doesn't where it came from, but this is my value function in the next step. Was then essentially I'm saying that instead of thinking I know exactly what my kappa eta is and being at a single point, I have some kind of a domain. And so, for example, a nice one, and I'll see this in the next slide, why this is so, but a nice domain to have will be some kind of an ellipse. And so this is my uncertainty set B. And what I try to do, I try to find the worst case. And the worst case means, the highest value function. Again, I'm trying to maximize, this is the worst case. And so I'll be somewhere here. This is the worst case. And then this is the kappa check, eta check I should use for my action. Okay, so let me clear this. It's gonna stay. Let's see. So it's gonna work. Yeah. Okay. How do I'll take some questions while I'll try to. I have a new bar now. So I can see that the value function will generally be monotone in kappa and eta, and so therefore the worst case will always be on the edge of my uncertainty set. Okay. So the main plan that we are doing in the second project is to think about adaptive robust, which is adaptive robust control. This was what Tao did in his PhD thesis together with Igor and Tom at Illinois Tech. So that's the idea of trying to learn and robustify jointly. And so the way this primarily works is that you have your uncertainty set is now state dependent. Okay, now how's it going to look like? Well, the idea of uncertainty set, and I'm going to have it on the next slide, is that this is reflecting some kind of a posterior uncertainty about your parameters. Now, again, we talked about linear dynamics of the problem I explained. And so if you think about the kappa and eta, again, my two key variables, then they're jointly Gaussian. And so the posterior is also Gaussian. And so any uncertainty set, joint uncertainty set, will be an ellipse centered around the best estimate, the a posteriori mode kappa head and eta head. So that gives you an ellipse. The ellipse, because of the correlation of the estimating the two parameters, is not axis aligned. That's why the ellipse has also an angle. So it has a sort of a non-trivial geometry of how those things look like. And this is capturing how this ellipse evolves over time as I move across periods n. So this is a function of n. The red dot represents the fixed true parameters, and the green is my estimates indexed by n. Okay. So here's the actual equations, how this looks like. So the posterior uncertainty set is expressed in terms of there's a 2x2 matrix, which is the posterior covariance matrix Mn, and there is another scaling factor Rn, and then you get the ellipse comes by thinking about some kind of a alpha quantile of the F distribution, which again comes out from having this bivariate Gaussian, and that affects the size of the ellipse. So the alpha here is controlling the size of this ellipse. How plausible you're willing to take. Is it a 95% posterior uncertainty set or a 99% and so forth. So from a linear regression perspective, the way to think about the evolution of your estimate in the learning is through this covariance matrix Mn, which is of course three-dimensional because it's symmetric. So it has the two diagonal entries plus the off-diagonal entry and the scaling factor Rn. So that sounds like it's a four-dimensional thing. But if you think about the ellipses, the ellipse will have a major axis, a minor axis, and some kind of angle of rotation. So actually, and there is a dependence factor, deterministic dependence factor hiding between M and R dynamics. And so in fact, it's a three-dimensional system from and so you have two different ways to do it: through the M and R linear algebra formulation, or through the geometric way of thinking about the major minor axis and the angle. From a Bayesian perspective, which is where this whole expression comes from, right? The underlying assumption is that there's sort of a true parameter that we're trying to learn, and so therefore naturally, what happens is that M's and R's kind of grow, and therefore what happens is that the ellipse shrinks over time. So you saw this here already in this plot here. So the ellipse gets smaller, so your posterior uncertainty decreases as n goes along. But you have a way to control this. So if you think this is not financially viable, you can modify this this rate of convergence to slow speed it up. Okay, so let's go back now. What do we have? So now we're going to do dynamics of our new system. Now our new system has the following terms. We have our estimates kappa hat and eta hat, and we have our other state variables m and r, which are controlling our ellipse. Because now our uncertainty set is state dependent, so therefore that affects we have to keep track of that to be able to do the worst case analysis in a time dependent and belief dependent format. So now I end up with a 7-dimensional system. I have my x and d as before. I have the center of the ellipse, kappa hat, eta hat. This is my best guess of what the parameters are. And then I have 3 more, which are the major minor axis and the angle, which are telling me how big my uncertainty is around my beliefs. So this is essentially a fine dimensional sufficient statistics exploiting the linear structure for my beliefs, joint beliefs about my 2 parameters kappa and eta. Okay, and so now I'm going to take all this and plug it back into my dynamic programming equation. And so I think I have about 6-7 minutes, and I'll stop there. So I'm going to plug this back into my programming equations. So my state variable now is 7-dimensional, y. My terminal condition is basically the same as before, but now in the algorithm looks very similar to how it started, except I have this modification here. So this is the only new bit, really. So if you stare at this as code, you'll realize that this looks exactly as what I had before when I talked about parametric or when I talked about adaptive. The only challenge now is that I have this worst case. So this is the robust piece. And the worst case is down the following. So in terms of the optimization part, it's just the worst case over the boundary of the ellipse because due to monotonicity. And in fact, as was actually seen in this picture here, the worst case is always about kappa being bigger than you expect and eta being kappa being smaller than you expect and eta being bigger than you expect. And so there's a half of the ellipse, which is definitely not the worst case, and the other half is you don't know exactly where you're going to end up. So you have that the worst case angle of the ellipse is 1D between 0 and pi. Okay, so otherwise everything else is the same. And again, what I try to do, I try to solve the local problem, plugging in the my transition G tilde, which is mapping those 7 variables. Now, what is G tilde doing? Well, G tilde is basically summarizing the evolution of the kappas, which are here. So this whole thing here is a part of the G tilde. Here's the dynamics how M evolves. Here's the dynamics how R evolves. And so this is all these things put together gives you how the overall the 7-dimensional state evolves. Ultimately, it only has still where the generator has only one exogenous epsilon driving in terms of the external shocks. Okay, so how would that how do we actually do this? Well, I call this whole thing here, right? I call this as a function. This is fixing everything else. I basically have f of u, which is my control, and then phi, which is my the worst case parameter. And so first what I do is I define f1 of u. This is the sup over phi of this thing, right? So this whole thing there, all of it is up to here is f. Okay, so I have f1, which is numerically computed as a sup over phi, and then I want to do I want to do an inf over u of f1 of u. So I have, and again, so this are implemented directly as is using fmin with one-dimensional variables. So I have a nested definitions that to get f1 of u, I have to do f1 is defined implicitly as a sup, and so this is just a nested bi-level optimization, but from a coding perspective, I just directly do that. So now again, I go ahead and I build a large collection of training input, and I pointwise compute the corresponding value function estimates V's and corresponding best actions use, and I save those. And then finally, I just go on and use that again to train my two surrogates, my neural networks for V and U. So the again, the pitch I'm trying to make is that the plan is exactly like I had for parametric. The only really modification is that I have a more complicated transition map and I have a more complicated local optimization to do. But otherwise, the conceptual logic just carries through. And this is again why we feel that the having this dynamic programming approach is convenient, because it keeps it very clear about you just modifying what is the local problem you're trying to solve. And the surrogates are only used solely for the purpose of patching together these local solutions into a global map functional approximation. Okay, so I need to stop in 2-3 minutes. So let me. This is a quick summary of how this looks like. So here is the ellipses, which change step by step. The worst cases are the squares, which move around. And then I have the circles are my centers of the ellipses, which move around. And then these are the actual. So I have some sort of an adversarial situation where the actual the true parameters driving my model are also changing over time. And so that is the type of environment I'm imagining where I want to be both robust and adaptive, where I know that I have some kind of unpredictable change of the true data generating environment. So I want to be protected against not know exactly what it is, but also I want to keep learning that I adjust my beliefs based on what I see. Okay, so I'm almost done. So just to recap, so there's actually a few more potential versions of how you can now put things together, because we have this three-way thing of we're doing optimization, but we're doing adaptive, which is about learning, and we're doing robust, which is about mitigating model risk. So the adaptive strategy is obviously overconfident because it's myopic. So it doesn't anticipate that your beliefs will change in the next step, and so it will tend to be sort of overly aggressive if present a situation where beliefs are wrong. The static robust situation is too conservative because it doesn't adjust to any learning. So essentially, the ellipse is essentially fixed forever, and so in that sense, it's a lower dimensional system, but it's obviously being too conservative because it doesn't take into account anything, any learning, any adjustment to what you see. Just to on the point of robust, the VBOP strategy is model free, right? So it's an open loop strategy which just says trade a predetermined amount, and so that's actually can be shown to be the optimal for if you have completely vague beliefs, you think anything is possible, then VWAP is your answer. And this is the other thing I want to mention for 30 seconds is with optimal execution, it's a very nice problem because you have the objective is fixed. You have to buy X0 shares. And so you don't have a situation where your strategy can be completely different because if you didn't buy it today, well, you'll have to buy it in the next couple of steps. And so it's not about some kind of authenticity in the actions. It has to be that, well, do you buy things more sooner or later? And so really the two extremes are the U-shaped curve, which is you really know exactly what you're doing, and the VWAP, which is constant. And this adaptive robust strategy are in some way interpolating between these two extreme situations. So there's more ways to have versions. For example, you can have something which is robust and adaptive, but it's myopic. So it doesn't actually use the programming equation at all. It just plugs in the base case parametric solver in here. And so it doesn't want to build surrogates. It just wants to figure out what's the, so it kind of does half of the job. It just does some kind of a computation for the control, but not for the value function. So it decouples this actor-critic link between neural networks. So the testing is quite interesting because if the environment is kind of benign, then being adaptive and robust is an overkill. it's trying to do too much, and so it's going to actually underperform. So you can easily see that if you have a correct initial beliefs and the environment is static, then just using the non-robust, non-adaptive strategy will actually be the best. So you have to have something which is adversarial, because again, if it's not adversarial, then the adaptive strategy will win out. And so we have a whole range of test environments where we can kind of tune those different knobs and see who comes out ahead across all these different control types. And so this gets into a situation where ultimately every model we try is misspecified, and we can kind of see how they react to the different misspecifications and what's how they compare in costs. So I'll stop with the sorry, I'm stuck. Okay. What is this not happening?
Thank you very much, Mike.
No, let me give you the last slide. So this is one plot to compare my different strategies. And again, this is the case where the non-robust strategies are buying too fast. They're buying too much here in the beginning. And so therefore they're going to pay the cost later, because once you buy, you cannot unbuy it back because it's a buy-only program. So then you're going to end up with being too aggressive. You cannot really correct for that. And so I'll stop here. So the first paper is on archive, and there's a link there to the Jupyter Notebook. The second one is coming soon. And then last thing, I just want to advertise, I have a review article which came out early this year, which talks about the bigger picture of how statistical machine learning and these different surrogates fit in different applications of in finance. Thank you.
Thank you very much. Any questions from audience, panelists? And then let me start with a quick question. You are talking about stochastic resilience effect. Epsilon is normally distributed, mean zero, variance sigma square. Is there any significant effect in the overall calculations at the end? What is the size of sigma square?
Yeah, sorry. Yeah, so in fact, I gave this talk somewhere else, and I had the same question before. So that's a common question. So this is one reason why I'm doing numerics, because the distribution of epsilon is completely irrelevant to the numerical side. It can be anything you want. So I mean, we started with a Gaussian because if it's Gaussian, then Moritz was able to do this linear quadratic computation, which is exploiting that to some effect. But otherwise, if you want to have heavy tailed or any other distribution for epsilon, that's totally fine. Again, what happened ultimately is that in the dynamic programming equation, you have to do the conditional expectation, which we're doing explicitly by just discretizing and also try Monte Carlo. It also works fine. It's just more noisy. So we feel given that the exogenous noise is 1D, direct this Gaussian quadrature or numerical quadrature is more stable and faster than having Monte Carlo. But both things work fine. So we're not doing anything special on how to compute conditional expectation. And in that sense, any solution for epsilon is fine. What is sigma doing? It's a complicated answer. So the effect of sigma is not obvious. And we have some plots in the parametric case. I actually haven't tried it in the adaptive robust. That's a good question. So I don't have, but we'll try it out.
Thank you very much. And there's a question in Q&A. Kami, could you explain your question?
Can you hear me?
Same question.
Yes.
In slide 21, I wanted to, if another distribution we need to convert to F, or model works, or does model
okay
work?
So if I think I understand correctly, you're asking about the F distribution or the whole equation for Bn. So what, let me try to answer. So the way this comes about is if you go back and you have you write down the linear regression equations for a bivariate unknown kappa and eta, and you write down the posterior, and then you write down the posterior alpha quantile, as a bivariate object, then you get this formula. So this is coming purely from that idea. And so, for example, that distribution is coming from the fact that everything is Gaussian, and this is the right thing to do for a bivariate Gaussian. So that is the motivation where this comes about. Now, at the end of the day, the BN is just something we impose, right? We essentially anticipate using this setup in a misspecified model anyway. And so this is something we essentially impose to say, okay, this is how we want our uncertainty sets to look like. Now, what we want from our uncertainty set, we want them to be state dependent, we want them to be centered at our best guess, and we want them to have reasonable dynamics over time, that they somehow, let's say, shrink if you think that this should shrink because you're learning and you get more information, you're getting smarter over time. So that's all you have to require. So obviously the other thing you want to have some kind of a finite dimensional statistics, right? And so this is a situation where my posterior uncertainty set together with my estimates is finite dimensional. It's only 5-dimensional, right? This is kind of the main trick from a numeric perspective, is that I end up with a 5-dimensional, which sounds quite bad, but it's for a neural network, it's quite reasonable object, which is again the center of the ellipse, the 2 axes, and the angle. So if you have some other way of coming up with a reasonable way of having 6-dimensional, 4-dimensional, 2-dimensional way to describe those uncertainty sets, such that they also change over time in a reasonable way, then this is totally fine, and the method doesn't really care.
Okay, thank you.
Now, the harder question would be, okay, you say, well, this is all kind of assuming the Gaussian dynamics. This is really based on that logic. So what happens if things are not Gaussian? Well, if things are not Gaussian, then you're going to end up with some kind of a infinite dimensional posterior uncertainty set. In fact, Tao has some papers on this in a non-optimal execution, but in a theoretical way of how this would go. But in fact, the method in terms of being well defined carries through. You can have some kind of a infinite dimensional uncertainty set as long as you can compute it and be able to optimize over it. Then you're okay.